Hello, my darlings. Okay, so today we're going to look at some properties of integrals. We're going to start with a simple basic problem before we get into the new properties that are going to manipulate this a little more. So what we have here is a graph of f of x, and it consists entirely of line segments and a semicircle, which is between -6 and 0, and it's on the closed interval from -8 to 13. Okay, so that's the graph we have. Now what we're going to do is we're going to evaluate some of these integrals. So the first one, definite integral, is the integral from 0 to 7. Now that shape that the curve makes with the x-axis is a trapezoid. So the area formula of a trapezoid is 1/2 times the height. Now the height is here, which is a height of 4, times the sum of the bases. Now the bottom base goes 1, 2, 3, 4, 5, 6, 7, plus, now the parallel base has a length of 1, 2, 3. So that's going to give us 1/2 times 4 is 2, 7 plus 3 is 10. This value is 20. Okay, next integral. That's the integral from 0 to 13. Now we've already found the area from 0 to 7. That was 20. Plus, now we need to find the area from 7 to 13, and that's another trapezoid. Now here's the problem. It's below the x-axis, which means I'm going to erase this addition sign, because if it's below the x-axis, we need to have negative area. Remember, an integral assigned area, so we put a subtraction sign. Area of a trapezoid is 1/2. The height, this is going down 1, 2, 3, times the sum of the bases. From 7 to 13, 1, 2, 3, 4, 5, 6. That's a base of 6. Plus the parallel base is also 3. So we have 20 minus 3/2 times 9. That's 20 minus 27/2. That's going to give us 13/2 or 6.5. Either one is okay. Yes, it is okay to break both of these trapezoids up into 2 triangles and a rectangle and find the area that way. If it's easier for you, that's fine. Not a problem. C, the integral from -6 to 0. Now that's our semicircle, but also it's below the x-axis. So since we're below the x-axis here, we have to have negative area, and the area of a semicircle is 1/2 pi r squared, and the radius on this circle is 1, 2, 3, so we have 3 squared. So this is -9 pi over 2. Great. Now we want the integral from 3 to 3. So if we start at 3 and we end at 3, we didn't move anywhere, we have no area, and we get 0. Yay! Same picture, just new problems. Okay? So now we have the integral from 7 to 0. Now when you're on a number line, we go from left to right. 7 is to the right of 0, so we need to reverse this order from 0 to 7, but if we reverse the order, we need to negate. So this is the negation of the integral from 0 to 7 of f of x dx. We can't go from 0 to 7, so this is actually going to be one of the new properties, which we'll talk about in a minute. Okay? From 0 to 7, that's that trapezoid that we found the area of in part A, only we're negating it this time so that it's -20. F has the same type of problem. We can't go from 10 to 4. We need to negate this and go from 4 to 10 of f of x dx. Now 4, so this is equal to the negation, 4 is here and 10 is here. So again, I have 2 trapezoids, or you can have 2 rectangles and 2 triangles, your call. I'm going to use, now I have to have this negative around all of it. So my top trapezoid is 1/2 the height, so 4 times 1/2 times the bases. The bottom base is 3, the top base is 1. Now the bottom trapezoid down here, it's below the x-axis, so I have to negate this. And it's 1/2 times the height is 3, so that's 3/2 times. This base here is 3, plus this base here is 2. So now I've got the negation of 2 times 4 minus 3/2 times 5 which is going to give me the negation of 8 minus 15 halves, which is the negation of 16 halves minus 15 halves, which is negative 1/2. All right. Now let's try the integral from negative 8, that's all the way here, all the way to 13. So we're doing everything. So let's look at this. This is a triangle. 1/2, the base is 2, the height is 4. So that area is going to be 4. 4. Now instead of adding the area here for the semicircle, we'd have to subtract it, right? And we already did that in part C, so I'm going to subtract the 9 pi over 2. Then we're going to add the area on this trapezoid from 0 to 7, which we did in part A, which is 20. And then we have to subtract the area of this one below, and we're subtracting because it's below the x-axis. So we're subtracting, and we did that one from 7 to 13. We did we not do it? We did it as part of a problem. We did it as part of B, right? We did that area right here, and we found that was negative 27 halves. So now a little bit of work here. We're going to have 24 minus 9 pi over 2 minus 27 over 2. That's going to be 21 over 2 minus 9 pi over 2, or 21 minus 9 pi all over 2, whichever way you prefer to write it. Okay, so now we want to find f prime of negative 6. Now, the derivative is, remember, this is the function f of x, so our derivative is the slope of the curve at negative 6. But if you look at negative 6, we have a corner, and if there is a corner, there is no derivative. So this derivative does not exist. Awesome. Now we want the second derivative at 6. Now remember, f of x is linear, right? It's a linear function here at 6. If you look at this piece where x is 6, that's a linear piece. So f of x is linear at x equals 6, which means the derivative of that is just a constant slope. So f prime of x is a constant. What's the derivative of a constant? Well, that's our second derivative, which has to be 0. There we go. Notice there's no concavity on a line. It's not concave up or concave down. That's because the derivative is 0 for that whole time. Now, an average rate of change of f from 0 to 5. We want to find f of 5 minus f of 0 over 5 minus 0. Now, if we look at the graph, f of 5 is 4, minus f of 0 is 0, all over 5 minus 0, which gives us 4/5. There we go. Same picture, new problems. True or false? What do you think? That the integral from 0 to 2, that area, plus the integral from 2 to 4, that area, is the same as the integral from 0 to 4. If we take this area and we add this area, we do get the same area here. So yes, this is a true statement, and this is going to lead into one of our properties that we're going to look at in a minute. One last question on this problem. Over which values of x is f of x not differentiable? It is not differentiable when you have corners or cusps, right? Or when the function doesn't exist. So that's going to happen at a lot of points on this. It's going to corner here, corner here, corner here, corner here, corner here, corner here, corner here. That's a lot of corners at x equals negative 6, 0, 2, 5, 7, 8, and 11. Nice. Okay, so now we're going to formalize those properties. So the first thing is that f and g are integrable functions. We can take the integrals. We're on closed intervals from a to b and b to c, and k is a constant. So k is some constant. Then the 0 rule tells us if we do the integral from a to the same number of a of f of x dx, that's 0. We saw that on the graph that if we do the integral from 3 to 3, we had no area under the curve, right? There was no area under the curve to measure. It's 0. The next one is the order of integration rule, and we talked about that in the previous problem also. The integral from a to b of f of x dx is the same as the negation of the integral from b to a of f of x dx. So we can reverse the order of the limits as long as we negate it. Now the constant rule we've already talked about, that if we do the integral from a to b of a constant k, I think we used c when we did the rule, the constant k of d of x, that's because remember, that's a horizontal line with a height of k, and we go from a to b, we'd have a rectangle here. Base would be a minus b times the height k. Remember that rule? When k is a constant, that's that integral. Now there is a constant multiple rule which says that if we have a constant times f of x, we can factor that outside the integral. That's nice and handy sometimes. A special case of that is when you have a negative in front of the f of x, you can factor the negative outside of the integral and it makes it easier to simplify. So the sum rule says if I do the integral from a to b of f of x dx plus the integral from a to b of g of x dx, that's the same as the integral from a to b of f of x plus g of x. So you take the integral of each part, okay? And it works the same way for subtraction. So if I have the integral of a difference, we take the difference of the integrals. The integral from a to b of f of x, don't forget your dx, minus the integral from a to b of g of x dx. Awesome. Now, there is something called the domination rule, which says that if g of x is always greater than or equal to f of x on the closed interval from a to b, then it makes sense that the area under the curve g of x is going to be always greater than or equal to the area under the curve of f of x. So the integral from a to b of g of x dx is greater than or equal to the integral from a to b of f of x dx. Now there's a special case of that. If f of x is always positive, then the integral from a to b of f of x dx is always positive or 0. Okay? Next one is the max-min inequality. And we don't use this very often, but it's nice to know that an integral has an upper bound and a lower bound. So if we let max f and min f be the maximum and minimum values of f, then that minimum value times the length of the interval, b minus a, would be a lower bound for the value of the integral. It's not going to get any smaller than that. And if we take the maximum value of f and multiply by the length of the interval, b minus a, that's going to be an upper bound for the value of an integral. And all values of the integral for x value will be in between those two, okay? Then comes the interval addition rule, and we saw that a few minutes ago in the true-false question. This, if you go back to that true-false, remember we said the integral from 0 to 2 of f of x plus the integral from 2 to 4. Notice these are the same number. It kind of links them together. The integral from 2 to 4 gives us the integral from 0 to 4 of f of x dx. So this interval addition rule says if I have the integral from a to b of f of x dx plus the integral from b to c of f of x dx, that's the same as the integral from a to c of f of x dx. And then we can also, if we know parts, we can use, so if I know the integral from b to c and I know the integral from a to c, or I know the integral from a to b, we can use them to find other things. We can manipulate this and we can subtract this from both sides, and we'd have the integral from a to c of f of x dx minus the integral from a to b of f of x dx. And there we go. So that's all the properties. We used a lot of them the same, over and over again, and then some we use less often. So here's an example. We're going to use the properties of integrals to evaluate each of the following, knowing that for this problem, the integral from a to b of f of x dx is 8, the integral from a to b of g of x is negative 3, and the integral from a to b of h of x dx is 5 over 2. Okay, so we want to do the integral from b to a of g of x dx. That's similar to this, but the order changed. So we have to reverse the order to get a to b of g of x. Am I allowed to just switch the order? I'm allowed to switch it if I negate it. That means my answer is the negation of this -3 or +3. Now the next one, we have a 2 times f of x. So I can factor out that 2 times the integral of a to b of f of x dx, which will mean I have 2 times this integral is 8, and my value is 16. Now I also have the integral from a to b of 5 dx. Now 5 is a constant, so that means this is 5 times the length of the interval b minus a, and that's our answer. Now I've got the integral from a to b of a sum. So I'm going to break this up into the integral from a to b of 5 dx plus the integral from a to b of g of x dx. Now we just saw that the integral from a to b of 5 dx was 5 times b minus a. And we know that the integral from a to b of g of x dx is -3. Here's our answer. And yes, you can write 5b minus 5a minus 3. That's also true. Very good. All right, next up, we have the integral from a to b of f of x minus g of x. So that means we're going to break up the subtraction. The integral from a to b of f of x dx, and then minus the integral from a to b of h of x dx. Well, we know that the integral from a to b of f of x dx is 8, minus, we know that the integral from a to b of h of x dx is 5/2. So that's going to give us, let's see, that 8 is 16/2 minus 5/2. That's 11/2. There we go, or 5.5. Next up, we have addition. Notice this addition problem. We have the integral from a to 4 of h of x dx plus the integral from 4 to b of h of x dx. Those limits are going to connect, and we can say that's equal to the integral from a to b of h of x dx. And we know that that value is 5/2. Done. Okay? Here's another problem. If we know that the integral from 1 to 5 of 3 times f of x plus 4 dx equals 34, we want to find this integral from 1 to 5 of f of x dx. All right, so I'm going to start with what I know, and this is an involved integrand, so we're going to break it up a little bit. Now, I can factor out the 3 because it's a constant, so that becomes 3 times the integral from 1 to 5 of f of x dx plus the integral from 1 to 5 of 4 dx, and we know that's supposed to equal 34. Now we have the 3. Do we know what the integral from 1 to 5 of f of x dx is? No, that's actually what I'm looking for. So we're going to be solving for this pink integral. But I do know that the integral from 1 to 5 of 4 dx is 4 times 5 minus 1, and this is all going to be 34. So now I have 3 times our integral. Now 5 minus 1 is 4, and 4 times 4 is 16, and that equals 34. So if I subtract 16 from both sides, now I'm going to have 3 times our integral equals 34 minus 16 is 18. Now if I divide both sides by 3, the integral from 1 to 5 of f of x dx equals 18 divided by 3 is 6, and we have the integral by ourselves. We're done. 2 more properties here. I want you to think about an even function. So an even function is a function that's symmetric with respect to the y-axis. So I'm just going to draw an arbitrary even function, right? And if I know that the integral from 0 to 3 here, that this is 8, okay? That's 0, that's 3. This is -3. What is this area over here? Well, since it's symmetric with respect to the y-axis, this is the same amount of area as we had on the right-hand side. So this is also 8, right? So that means that the integral from -3 to 3 of f of x dx is equal to twice the integral from 0 to 3 of f of x dx. So this is 2 times 8, or 16. So it's nice to know when you have an even function that if you know the value of the integral on one side, you can double it to get the whole. Now, what about an odd function? Now, odd functions are symmetric with respect to the origin. So let's take a basic function, even let's just make it a linear function here, okay? And if we know that from 0 to 3, we have area here that is 8, what happens when you go from -3? What do we know about this area? Now, the area is still 8, but the integral is going to be -8 because it's signed area. So that means that the integral from -3 to 3 of f of x dx, if I add that up, that's 8 plus a -8, that's just 0. So odd functions, the areas, the positive area and the negative area, are going to add up to 0. All right, guys, there we go. We've learned some properties of integral, and we practiced finding areas. Have a great day, guys. See you soon.